Hello everyone, welcome to my video. We will start chapter 2 in this video with the rectilinear motion. Recall the difference between kinematics and kinetics we talked about. Kinematics focus on the motion itself, and at this point we do not care why the object is ended up moving. Since there is no reference made to forces, at this stage acceleration is mostly given, either as a straightforward value or a function of time or distance. So we are not going to explore 3D motions in this course. In 2D, there are several choices of coordinate systems we can use. We will explore them one by one later on. There are two reference frames that we will be working with back and forth throughout this entire course, absolute and relative. When we are interested in absolute motion, we will set a fixed reference system, examine how things are moving within it. When we are interested in a relative motion, the reference system is set to on the moving object or a plane. Then we will examine how things are moving relative to the moving object within the plane. The word rectilinear, there is a linear in it. It means straight lines. There are three basic parameters and they are important: displacement, velocity, and acceleration. They are all vectors with magnitude and direction. When solving problems, make sure you stick with the sign convention you set up. Usually you should do this at the very beginning. For example, the common sign convention is right and up are positive directions for x and y, and the counterclockwise is positive for moments. However, sometimes we will improvise with this. Your x-axis may not be horizontal. Calculating the difference, or delta, in this course, whenever you are calculating a difference between two stages, it is always final minus initial. Always. No exception. Please keep this in mind as it will help you to stick with your sign convention so you don't end up with mess up with the negative sign in your final answer. Using displacement as an example, displacement comes from changing positions from P to P prime. A fixed position itself is not meaningful to us. We are interested in how the particle moves from one position to the other, which can be measured by displacement's delta S, which is the final minus initial, P prime minus P. So your displacement is positive 1 in this case, which means the direction is to the right by 1 unit. Let's look at the velocity and acceleration together. Velocity is measuring how fast the displacement s is changing, and the acceleration is measuring how fast the velocity v is changing. They have different units, of course. Velocity in meter per second or feet per second, acceleration in meter per second square or feet per second square. They can be calculated as average values, which is measured over a period of time, or they can be calculated as instantaneous values by taking time derivatives. Since acceleration is a time derivative of velocity and velocity is a time derivative of displacement, we will also often use the double derivative of displacement, which give us the acceleration as well. Finally, the sign convention. Please be careful. This is the third time in this video I'm mentioning it already. Sometimes, instead of giving you a value or function, you will get a graph, such as this ST diagram here. In this example, we have s equal to t. Take the derivative once will give us the velocity, which is 1, the slope. Take the derivative again, we will get acceleration, which is 0. The other way to look at this is a slope of s is v, or slope of displacement is velocity, and the slope of v is acceleration. Another example here, s equals to t squared. Again, by taking the time derivative one step at a time, we can get the velocity 2t and acceleration t. In this course, especially at the beginning few chapters, we will be doing a lot of calculus. So make sure you review those skills you learned in the past if you are a little bit rusty about it already. We talked about slope. Then we can talk about the reverse operation of taking slope, which is area under the curve, or integration. Recall we've got the v equals to 2t on the previous slide. So calculating the area under the AT curve will give us back the velocity, in this case, which is a 2 times 2 equals to 4 meter per second. In the integral form, we have a dt equals to dv. Going backward again, we can take the integral of velocity, which will give us back the displacement. Using the area under the curve again, we have a triangle. 4 meter is the answer. Recall we had s equal to 2 square. Subbing the t equals to 2 give us the same value. So here we have v dt equals to ds. Given the two simple examples we looked at, let's consider its general definition here. Velocity at time t is a slope of the position curve at time t, and acceleration at time t is a slope of the velocity curve at time t. The area under the vt curve during time interval from t1 to t2 is a net displacement of the particle during that time interval, and the area under the AT curve during that interval is a net change in velocity of the particle during that time interval. So this is the same as what we did, but just in a more generic form compared to the examples, the two simple examples we looked at. Now we can combine the two time derivatives of displacement and velocity to eliminate the dt part in them. Then we got an alternative form that is not involving the time variable at all. This is a very important relationship. I'd say this is probably more important than the original form ds over dt or dv over dt. Based on this adv equals to ads, VS diagram also exists, but we rarely use it, so we will not explore further here. In the next few slides, we'll look at some common scenarios you will encounter when solving problems. The first one is the most straightforward scenario. St, the displacement is a function of time, is given. This is the same as we saw in the previous example. If this is the case, then great. We will just go ahead to take the time derivative of the function to get velocity and acceleration. Sometimes, if you see a very nasty function, check out the diagram. Most of the time, the diagram will also be given. Remember, you can also use the diagram to calculate the area under the curve to get the value that you want. In this case, if you are given a constant acceleration, you should also look for t0, s0, and v0, those initial conditions or boundary conditions. With these variables known, the generic relationship we obtained before can be simplified to deal exclusively with constant acceleration questions. For example, given a equals to 2 meter per second square, t0 is 0, s0 is 5 meter, we start at the 5 meter mark, v0 is 3 meter per second, that's our initial velocity. After 5 seconds, we can calculate velocity. We can calculate the displacement, which is 13 meters per second and 45 meters for displacement. So I'd like to pause here for a few seconds to look at the last equation here. This equation, it's derived from VDV equals to ADS. It will be especially useful when the time is not given. Then, if we were given the acceleration as a function of time, we will simply modify the original relationship again, but not getting rid of the integral anymore since we have a function of time. So given known boundary conditions, we would be able to calculate v and s. For example here, given acceleration is 12t, a function of time, meter per second square, given the initial condition t0, s0, v0 are all 0, we can take the integral going back to get our velocity is 2t squared and displacement is 2t cubed. The next scenario is the acceleration can also be given as a function of velocity, a equals to fv, a function of velocity. If that's the case, then we'll need to use the third relationship as we developed before, VDV equals to ADS. Given proper boundary conditions, don't worry, we'll always give you. We can calculate the displacement through this equation. For example here, given acceleration is a function of velocity 10 minus 5v squared, given the t0, s0, v0 initial conditions, we can use vdv equals to ads to take the integral to get our displacement is negative 1 over 10 ln v squared minus 2. So the last common scenario you may see is the acceleration is given as a function of position or displacement, a equals to fs. Once again, you will be given those proper initial conditions, such as S0 and V0 in this case. Using this equation here, we can calculate velocity. For example, given this a equals to 2s squared, subbing the initial conditions T0, S0, V0, we can calculate V squared can be represented as 4 over 3 s cubed. Okay, so that's the basic 4 or 5 scenarios you will see. It's kind of exhaustive to show all of them. So we have covered a lot. Is it overwhelming? Maybe. I know. We have lots of equation, lots of integration, differentiation, just a lot of calculus. However, taking a step back, they are all derived from these 3 basic relations with 3 basic variables, s, v, and a. The 5 scenarios we looked at is listed here, and all of those equations we're going to use in any of those scenarios are derived from those 3 basic parameters and 3 basic equations. If I can give you any advice, please, when solving those problems, be patient and do more practice. Starting this video, I will make a recommendation at the end on what sample problems in the textbook should be reviewed. These sample problems will not be discussed in class or here, but they are considered as required learning materials for this course, same as those practice problems we do in class and tutorials. All right, thank you for watching. I'll see you next time.